All right, welcome back to week one. Lots and lots and lots of videos. You think it's too many videos? Maybe. We're gonna pare down what we do in class. All right, so let's see where we at. We have a numerical example. This is from Dr. Bob Summers' notes to accompany the introduction of vibrations with applications. All right, so we have a 300-pound electromagnet that holds 200 pounds of scrap. I'm going to draw this as we go along so we can picture it, right? So let's see, it's got like a cable. What happened here? I think I picked white. All right, so we have a magnet. And it's got a bunch of scrap on it right there, right? And the cable keeps going. So there's the cable. So this is 300 pounds, and this is 200 pounds. In addition to the weight of the magnet, the current is suddenly removed, and the total equivalent stiffness of the cable is 1,000 pounds per inch. And you want to know the frequency of the oscillation and what is the minimum cable tension. So I had a question on that. I meant to ask him, I would think that we were asking for the required cable strength. I think that's what he means. And then what is the design operation implication of the answer? Okay, we'll see. So first off, what's going to happen is this: when this thing lets go. Okay, so first, so you're going to start with statics. And boom, 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 boom. The cable tension is kind of obvious, but we'll do it anyway. Got nothing better to do, right? No, that's not true. We have 300 pounds, and we have 200 pounds. So I know it seems silly, but tell you what, you can save yourself a lot of headache in life by drawing a free body diagram, even when it seems silly. I want to make mistakes. So the cable tension, Ft minus 300 minus 200 equals 0. The cable tension is a surprising 500 pounds. We knew that, didn't we? But what we can find there is how much of displacement. And the displacement is going to be the cable tension. Am I going to do this right? I think so. Divided by the stiffness. So that's going to be the static, but it's also going to be the initial, right? So we're going to start out by having pulled this springy type of thing down. So it's just a spring and a mass. So we have pulled it down. How much? We pulled it down 500 divided by 1,000. So we brought it down an initial displacement of I think my numbers are wrong. I'm sorry, 1,000 pounds per inch. Okay, so that's fine. We pulled it down. How many inches? 0.5 inches, right? Yeah. Sure, 0.500 inches. Which, by the way, should be 1.667 e to the minus 2 feet. I prefer to work in feet. I don't know why I just wrote F that right there. Feet. All right. So, yeah. And so the frequency of this oscillation is going to be 1 over 2 pi square root of k over m. But remember, these are in feet, right? So, I mean, these are the k is in pounds per inch. So this is a good practice, at least for me, I think, is to turn this into, and I hope I did this right, into pounds per foot. So I think you multiply it about by 12, right? So that's pounds per, that's 12 inches per foot. Yeah, so yeah, that gets the right 12,000 pounds per foot. And then here, when we get over to here to make the units match, we need the mass. So we get the 12,000 pounds per foot. Divide the 300, because the only thing that's left on there, the 200 goes away. The 200 caused the deflection. Oh, wait. I think this should have been 200. Because it's moving it from its equilibrium position. Its equilibrium position is with 300, but it's the 200 that has displaced it. So that makes, whatever the hell that makes, it only makes 0.2, dummy, 0.2. And now my inches, and now my answer makes a lot more sense. Okay. But now we're at the mass of the thing is the 300 pounds. And we're going to divide by 32.2 feet per second squared. Now we remember that when we do this, that'll turn these into slugs. Yeah. So we needed to turn those into slugs. So when we get down into Fn, I want to try to, yeah, okay, so here you go. Let me fix it. Pounds cancel, feet cancel, and now you have the square root of seconds. Yes. Okay, so it will work out unit-wise. And we end up with 1.954 hertz. And that's what I think the answer is. So the period is going to be 1 over that. And then in order to find the cable tension, to find what is the minimum cable tension, I think what you have is what's going to be the maximum cable tension, which is going to happen when it's on its way back up, right? And you can find this from doing the FBD and IBD of the thing, right? So you have the, here's your thing. Do the FBD, the IBD, X and Y, and here's your downward mg, or we actually just weight, the weight of the magnet, and then we go the cable tension, and then of course it's bouncing back up and down. There's no damping to stop the thing, so at some point it's going to be coming back up right there, and that's its acceleration as it comes back up. And that acceleration, by the way, is going to be related to x is equal to x times the sine of omega nt, x dot, x omega n cosine of omega nt, x double dot, x, well, it's going to be negative, omega n squared sine. So that's going to be that acceleration right there, which we can find. We should have taken omega n and taken 2 pi fn that we had before, which was 2 pi 1.954, and it should equal 12.27 radians per second. So we'll get x double dot is going to be equal to, well, we had the deformation, right? Ooh, did I do that wrong? No, I decided I did it right. I'm going to double check it with Dr. Bob. That I got that point. Yeah, that 1.667 E minus 2 times 12.27 squared is going to be 2.511 feet per second squared. All right, so that's what I'm going to use for that A right there. And coming back up to this right here, we go the sum of the forces in the y direction, mass times acceleration in the y direction. Up is positive. So we'll take Ft minus the weight of the magnet equals the mass of this times the acceleration. So Ft is going to be equal to, the weight of the magnet is 300 pounds plus 300 divided by 32.2, because this mass needs to be in two slugs, and the acceleration of 2.511, and you will get a total force of 323.4 pounds. So if I was going to ask answer the question, based on my understanding of what he's asking, what is the design operation application of the answer, is that, well, we had a 500-pound tension when we were when it was on there. Well, we would let go and it snapped back up. Its maximum was 323.4 pounds. So let me think about that. Is there any scenario under which? Well, I decided to go ahead and say, hey, if we wanted to like make a comparison, I would say that that we were 1.08. I made it like a factor of safety type of thing. But I don't know if I want to call it that, because you have to be careful using that word, factor of safety. We'll see if you're an ME350. We'll see how important our factors of safety are. So I haven't checked this actually against Dr. Bob's answers. So maybe I should have done that before recording a video, but I didn't. So here it is. So there you go. I'm sure I made a mistake somewhere.